This is topic 1, motion in a circle. We're going to look at centripetal force first of all. Consider an object moving in a circle at constant speed. Since the direction of motion is constantly changing, its velocity must be changing. And changing velocity implies acceleration. And this, of course, implies the action of an unbalanced force. And there are different sources of the centripetal force. For example, the Earth moving around the Sun, the gravitational force is the ultimate source of the acceleration, the force that provides the centripetal force. Now, this force is always acting towards the centre of the circle, and hence the name centripetal force, which means centre-seeking in Latin. The centripetal acceleration produced acts in the same direction as that force, that is towards the centre of the circle. The instantaneous velocity is always tangential to the circle, and you can see that in the diagram below. The velocity is at a tangent to the circle. The force and acceleration are always perpendicular to that velocity direction, so we can draw that in as a 90-degree angle there. Slightly better colour and size. Okay, so now we're going to derive the equation for centripetal acceleration and a centripetal force. We consider an object moving in a circle from point A to point B at a constant speed in a time delta t, and that's shown below in the diagram. The arc length which the object will move through AB, from A to B, will be equal to the speed v times the time taken delta t. Now we can also consider the velocity. That's the speed with direction at each point, and you can see that labelled on the circular diagram there, VA and VB. The change in velocity, delta V, will be equal to the final velocity minus the initial velocity, and that's shown by the expression VB minus VA, which of course is now a vector sum. So being a vector sum, we can draw a diagram, being careful to change the velocity VA around, so we have minus VA, adding it to VB to find delta V. You can't quite see that, but that's delta V. And that acts towards the centre of the circle. Now this triangle is similar to triangle AOB, which means the ratio of their lengths will be the same. So we can write this expression here, where we say delta V over V is equal to AB over AO. AO is the radius of the circle, of course, so we can actually replace that with the radius r soon. And the other thing is we can find an expression for AB in terms of speed and time. If we consider the angle to be quite small, that's theta, then the arc length AB will be approximately a straight length AB, and that'll be equal to V times delta t. That should be in that bracket there. So we continue to derive the expression by equating those things. We replace AB with V delta t and A0, A0 with the radius r. Rearrange slightly so that we have this expression, which of course means we have now found acceleration on the left hand side as equal to v squared upon r. And if we now simply multiply both sides by mass, using the idea that the force is equal to ma, then we can easily derive the centripetal force formula as mv squared over the radius r. Okay, so here are two examples to try. The first question is asking you to find the centripetal acceleration, and the second question asks you to find a centripetal force. The answers are shown, so you should be able to get these two answers here if you apply the formulae correctly.